Welcome. Welcome to part one of Earthquake Lecture for Earth Science, Bakersfield College. I would like to today start with the earthquake lecture, and we're going to discuss some areas of earthquakes. For example, what does an earthquake represent? In fact, what really is an earthquake besides shaking and moving around? What causes earthquakes? We'll discuss a little bit in this lecture how earthquakes are measured using the various scales like the Mercalli's, the Richter, and the moment magnitude scale. And then towards the latter part of the discussion, we'll look at predictions of earthquakes and how earthquakes are presently predicted today. So this is part one of the earthquakes, and certainly be followed by part 2, 3, and so forth. This first slide that you're looking at is a slide of the Oakland, San Francisco Bay Area earthquake in October of 1989. And this looks like the Highway 880, which I believe is the Bay Bridge. And you can certainly see that the damage where the bridge collapsed and fell onto the next level. And I remember this earthquake back in 1989. I was living in the Santa Barbara area, and I was just getting ready to watch the World Series when this earthquake occurred. So later on in the discussion, we'll revisit my time in Santa Barbara and during this particular earthquake. So a couple questions to look at in today's discussion, and that is you should ask yourself, have you ever felt an earthquake? Well, certainly if you've lived in California long enough, at least 5 years or more, you probably have felt some type of earthquake. And typically what folks feel is where you move side to side and up and down, and there's a rhythmic shake to a typical earthquake. And later on in the discussion, we'll talk about why that is. And again, we'll try and answer the question, what is an earthquake? Here are some earthquake statistics, and this will actually let you know how dynamic and how active your Earth really is, especially with plate tectonics and moving continents and so forth. But if you look at the earthquake statistics, 30,000 earthquakes strong enough to feel annually. Of those 30,000 earthquakes, 75 are significant each year. So these are the typical earthquakes that range in magnitude from 7 or 8, even maybe an occasional 9 magnitude earthquake. And these are typically the ones that make the news. Here are some significant earthquakes that have happened throughout history. 1960, the southern Chile earthquake was a 9.5 magnitude. The Alaskan earthquake of 1964, magnitude 9.2. And then the Sumatra earthquake of 2004, magnitude 9.1. And you'll notice that each one of these magnitude earthquakes are in the nines. And we're going to find out later that earthquakes, magnitudes 8s and 9s are very, very significant with respect to the amount of shaking and energy that is typically released. Here are some pictures now that look at some of those historic earthquakes. Here, the 9.2 Alaska earthquake in 1964. And here you can see where the street has basically been disheveled and lifted up and separated. And in fact, this earthquake of 1964 actually lifted the entire peninsula of Alaska up 4 feet. So think about the amount of energy that's required to lift that entire peninsula, the entire state of Alaska. Here's the 9.5 southern Chile 1960 earthquake. And you can see pretty much total destruction in the area. And then down here is the 9.1 Sumatra earthquake in 2004. And really the only difference between the Sumatra earthquake and the Alaska and southern Chile is the fact that the Sumatra happens to be in color. And so certainly the damage and devastation from these huge earthquakes are common. Most significant earthquakes, especially the ranges in the 8 and the 9 magnitudes, are typically earthquakes as a result of subduction and subduction zones and subducting of plates and so forth on convergent boundaries, will typically yield pretty large earthquakes in the 8s and the 9s. So how are earthquake vibrations similar to a rock entering water? So I like to look at an earthquake in terms of defining what an earthquake represents as throwing a rock into a pond. So in this slide here, picture the pond as the surface of the pond is very smooth, not moving, very calm. And as you toss a rock and the rock enters the pond, you would expect then ripples to emerge on the surface. So right here would be where the rock entered here, and maybe in this case, the rock entered here. And you can certainly see a propagation of ripples that now extend across the surface of the pond. And this really is a really good example of how an earthquake reacts when a sudden release of energy takes place on the Earth's surface. So when we describe an earthquake and define an earthquake represents vibrations within the Earth from a rapid release of energy in the form of seismic waves. So again, as that rock enters the surface of the pond, there's a sudden release of energy, and that energy is converted into waves. And in this case, we're going to refer to those as seismic waves. So for example, if there was a little frog out here on a lily pad and the rock entered the surface of the pond here, the waves would emanate out from the center point of that rock where it hit the water, and then that lily pad would have a tendency to go up and down. So the frog is sitting here going up and down, wondering, wow, what's going on? A lot of shaking. This is a picture of the San Francisco area in 1906. And this is damage as a result of the 1906 earthquake, which actually was moved along the San Andreas Fault just south of San Francisco. And certainly you can see a lot of damage that has taken place from that earthquake. And really, it wasn't the structural damage that really destroyed the city as much as it was the fires that came after the earthquake. And gas lines ruptured, and so the fires were a huge contributor to a lot of the damage. Here you'll see some pictures that represent the July 21st, 1952 Bakersfield earthquake. And here you see a picture of 19th Street in Chester. And you can certainly see damage from that earthquake. I believe that earthquake was around a 7.1 magnitude earthquake. 23 miles south of Bakersfield, you see more damage here. That's because this is the Arvin area, which was a lot closer to the epicenter in July 21st, 1952. Then here's another picture of 19th Street in Bakersfield, and certainly you can see the damage. And then here is just to kind of give you a mindset of a chair falling over during a very small earthquake. So Bakersfield area where we live is very susceptible to earthquakes, just like most areas in California. This particular earthquake came from a fault line just south of Tehachapi near Keene. So if you drive up Highway 58, and as you make your way up to the Tehachapi area, Highway 58 will go past Keene, and that's where the White Wolf Fault exists, which is still active today. So it's probable that at one point it could move again, and certainly certainly Bakersfield will feel the wrath of the seismic waves released. So a little bit of some earthquake terminology, and these are essential terms that we use to describe an earthquake. And the first term that we look at is the term focus. And focus basically represents the actual rupture that takes place. And 98% of earthquakes that take place on the Earth's surface are some depth or within the subsurface or below the surface of the Earth. And so the focus then represents that actual rupture. And so here in the diagram, you can see the focus located at some depth below the surface. The next term is probably a term that most folks are familiar with. This is known as the epicenter, and the epicenter represents the rupture point on the surface that is directly above the focus. And by definition, we're saying that that is 90 degrees above the focus. And epi, the word epi, really means surface. And so this is really saying surface center. So if you see the focus here in the subsurface, the rupture takes place, energy is transferred up to the surface, and at that point, reaching the surface, then that now becomes the geographical location of the epicenter. And then, of course, we've already talked a little bit about seismic waves. And seismic waves represent the vibrations that are released from this sudden release of energy when the land mass moves. And again, these vibrations come in the form of waves. If we go back to the focus and we say earthquake takes place here and then releases the vibrations make their way to the surface. And then once it hits the surface, it spreads out laterally along the surface. And so this really resembles that rock hitting the surface of the pond. So we could say, well, if we watch my arrow, we throw a rock, the rock comes in, hits the surface of the pond, and then the waves will kind of radiate outward and so forth. So I'd like you to take a look at this animated diagram, and I want you to describe to yourself what is happening. Most students will say, gee, this tree is falling over. And yes, that is true, but if you look at it a little bit more in depth, you'll find that the tree doesn't fall over immediately when the movement of the earth takes place. In fact, what you should be observing is that the land masses on this side and this side are both moving very slowly. And as they move, they're building up more and more pressure. And so at this point, it's building up more and more pressure between the land masses. And then the rocks will reach some point in which they can't take the pressure anymore. Then right here at this point, they will snap. And upon snapping, they'll release energy and you'll have breakage either in the subsurface and usually translated up to the surface. And this is known as what we call the elastic rebound theory. So in this particular slide, the animation is describing the elastic rebound theory. And so the way the elastic rebound theory works is we can kind of follow along the bullet points, and which really will describe that previous slide. So again, typically before an earthquake takes place, stresses begin to build and strain the crust. And really what this means is the word stresses means pressure and strain means deforming or deformation. So this says pressure begins to build, and as that pressure is building, deformation in the crust begins to take place. And then if we continue that stress, and as we continue that stress, the pressure is building and building, which is storing energy. And this type of energy, for folks that have had physics, is a type of energy called potential energy. So continued stress builds potential energy. And as the energy builds and builds, it begins to reach what we call the elastic limits of the rock. And when we say elastic limits of the rock, we're saying that the rock has reached a point in which it cannot hold the pressure anymore. And once the rocks reach that elastic limit, the rock will snap in response to all of the pressure. And that pressure then releases stored energy, and now it's in the form of seismic waves, or in other words, it releases kinetic energy. So rocks that store energy is potential energy. Once it snaps, it now becomes kinetic energy. And typically what happens is that rocks begin to reposition themselves back into place after a major earthquake. And that repositioning of rocks within the subsurface produces a series of what we call aftershocks. And by definition, an aftershock is typically a magnitude number that is less than the greater magnitude that first took place during the earthquake. So once the rocks snap, it releases a series of seismic waves or vibrations. And there are four major types of seismic waves that are released. And we can kind of split those four waves up into what we call body waves. And the body waves are what we call P waves and S waves. And then these are typical waves that will primarily propagate through the interior parts of the earth. And certainly they are felt on the surface, but again, they can propagate through the interiors. And then there are the surface waves, which are the L wave and the R wave. And these are primary waves that we feel, or dominant waves that we feel on the Earth's surface. So, what measures the vibrations then that propagate across the surface? Well, what measures the propagation of seismic waves is an instrument known as the seismograph. And the seismograph is an instrument that, in this particular example, is a very rudimentary type seismograph. And what you see is that this seismograph is bolted to the surface, and then hanging from the seismograph is a cable with a very, very heavy weight, in which we would say possesses a lot of inertia. In other words, it's hard to move. And then if you pass a paper underneath this heavy weight with a little tiny pin on the end of it, then what we would envision is that the surface of the earth would go back and forth, and that motion is dampened by the inertia from the heavy ball. And then you pass the paper underneath it, and it produces this squiggly lines on the paper. And this is known as a seismogram. So a seismograph will produce a seismogram. And one can glean a lot of information from the seismogram. It can interpret where the epicenter is located. One can interpret the size of the earthquake in terms of the magnitude. And again, one can interpret how far the seismograph station is, in fact, from the epicenter of the earthquake. So we're going to now spend some time and talk about the characteristics of each one of the vibrations that are typically released from an earthquake. And the first vibration is known as the P wave. And the P wave represents the primary wave, which has a compressional type wave motion beneath the Earth's surface. And that compressional wave, as it's traveling and propagating through the subsurface, will have a tendency to compress and expand the rock material. So, for example, come down to the bottom of the slide and look at the animation. And what you should see is the P wave is passing through this particular type of material. And you should look right at this little square right here. And as you see the P wave pass through, you notice that the square is being compressed, and then the square is being expanded. And what's interesting about this compressional vibration is that really the volume of the material that you're looking at really doesn't change. Instead, the wave is a vibration passing through the material. Now, because of the compressional forces behind the P wave represents the fastest of the three seismic waves, meaning that it typically will travel about 6 kilometers per second in the upper part of the lithosphere or the crust. And how fast is 6 kilometers per second? Well, that's probably just around a little over 3 miles per second. So when you say 1001, that P wave, compression wave, has already traveled 3 miles. And so case in point, we revisit the World Series game back in October of, I think it was 88. And we find that I was sitting in Santa Barbara getting ready to watch the World Series. And they had cameramen now are in the Bay Area, filming the World Series, getting ready for it. And so the earthquake took place up in the Bay Area. And as I was watching the television, the cameramen started to go back and forth, and they would say, "Wow, we're having an earthquake. Now remember, I'm living in Santa Barbara, which is probably about maybe 300 miles or so from the Bay Area. And within just 30 seconds, 45 seconds or so, Santa Barbara started to shake. And that tells you how fast these vibrations will propagate through through the Earth's surface. The last bullet point on the P wave is very important. And you look down here, and because again of the compressional type nature of the P wave, it'll travel through both solids and through liquids. So in other words, solids can be compressed and so can liquids. All right, so P wave, compressional wave, fastest wave, travels through solids and liquids. The next type of vibration that is released along with the P wave is the S wave, or the secondary wave. And what you have to envision is during an earthquake, the waves are released at the same time. It's kind of like watching horses in a horse race. And the horses are all lined up at the gate is lifted, and the horses all jump out at the same time. And that's really analogous to the vibrations or seismic waves when an earthquake takes place. So we have this S wave, the secondary wave. This is known as the shearing wave. And in this case, the shearing waves moves particles up and down, typically at right angles to each other. So again, if we come down to this animation, you look at the black square in the subsurface, and an earthquake is released. Here comes the S wave, and you can see how the black spot moves up and down, like shearing, or like taking a pair of scissors and moving the scissors up and down and shearing. And that's unlike the P wave, because recall the P wave is a compressional wave that compresses and stretches. So because of the secondary type motion or shearing type motion, the P wave or the S wave is about 2/3 the speed of the P wave. So we would just say the S wave is slower than the P wave. And it typically moves about 3.5 kilometers per second. And because of the shearing type motion, the S wave can only travel through solids. It does not travel through liquids. Let me repeat that. The S wave will travel through solids and not liquids. And why? Well, because remember, the S wave has a shearing motion. So it's very hard to shear a liquid, for example. The analogy to use is a pair of scissors. And when you cut with scissors, you're basically shearing. So my question is always, have you ever cut water? And if you think about that, you know that water, liquid water, does not cut. The last set of waves we'll look at, vibrations, will be the surface waves. And this is a combination of what we call the L wave and the R wave. And in this case, we call it the love wave and the Rayleigh wave. So the love wave exhibits horizontal motion similar to the S wave. But what's important is when we say horizontal motion, we're talking about a shearing effect on the surface. Because remember, the S wave is shearing up and down right angles in a vertical view. But we look at the L wave or the love wave, and it shears in a horizontal plane. And so it goes back and forth on the surface. And so during an earthquake, many folks will experience a shifting of side to side type movement. And that really is from the L wave. So the surface waves both travel the slowest of the four waves presented. So it's much slower than the P and the S wave, and again travels along the surface, producing a horizontal motion. The Rayleigh wave, on the other hand, travels similar to an ocean wave, meaning that it gives an up and down type of motion. And so kind of envision yourself on a boat, and you're sitting in the lake or the ocean, and the boat is anchored. So the boat's really not moving, yet it goes up and down because the ocean wave itself is passing underneath the boat. So the Rayleigh wave basically does the same thing. as it passes underneath the object that's on the Earth's surface. These two animations show the effects of the L wave, the love wave, and the effects of the Rayleigh wave. And what you need to take notice is if we look at the love wave, look at the square that's located on the surface, and as the wave is released from the earthquake, it comes down and it moves the square like one shaking out a carpet. And so as you shake out a carpet, you're basically producing love waves. But at the very end of the animation, you will see that you have a side-to-side shearing motion in the horizontal plane. Another observation to make on the love wave is let's pretend hypothetically that this little black square represents Bakersfield, California, and this area right here represents the San Andreas Fault, which we're only 70 miles from. And as the San Andreas Fault releases, it will release the seismic waves. And I want you to watch what happens to Bakersfield as the L wave passes through Bakersfield. And right there, you can see that basically it's like taking, again, that carpet and kind of shaking the carpet out. Now, I always ask students, have you ever body surfed in the ocean? And a few students will raise their hands and say, yeah, I've body surfed. And I'm saying that during an earthquake in Bakersfield, get ready to body surf on land. And certainly you can kind of observe that and see that as this L wave passes through Bakersfield. The Rayleigh wave, on the other hand, again has that particle rolling motion similar to an ocean wave. And here the wave is passing through the surface, but at the very end, you kind of look to see where the wave produces an up and down motion at the end of this block here. And so the Rayleigh wave is pushing right there, the up and down motion. So really, during an earthquake, one experiences from the surface waves of an earthquake, you experience a side-to-side motion and an up and down motion as well. This next animated slide shows all of the waves at the same time. And so if this slide can stay in synchronization, you'll see that the P wave gets there first. Well, it's a little bit out of sync right here. But the P wave would get there first, followed by the S wave, and then followed by the slower surface waves. So again, you can see the compressional motion of the P wave here. You can see the shearing motion of the S wave there. You can see the horizontal shearing motion of the love wave here. And then you can see the Rayleigh wave and up and down at the end of this diagram. So we'll kind of sit there and watch that for about 5 seconds, and you'll get a sense of what happens during an earthquake with respect to the types of waves that are released.